Hello, everyone. Today's Wednesday, November 26th. This is week four, class three of India evening and weekend platoon. Jordan's at a wedding, so I switched some days with him. That's why you get me 2 days in a row this week. Remember, no class tomorrow because of Turkey Day, and then you have class on Saturday, 8:30 Central. On Saturday, the morning is review, Python review, and then you will have your assessment in the afternoon. Typically, they release it around one, I think, normally. And you'll have the weekend to do it, and then it's due first thing Monday. Any questions about that? No? Pretty self-explanatory? Yes?
You said it's due Monday?
Yeah, I'll do
Or
Monday. Typically, you get the weekend to do it.
okay.
It's typically due Monday before class starts. Alrighty, just keep that in mind. Definitely, I would definitely have a day and a half or so. Don't plan anything for Sunday, probably. Um, yeah, small tip there. Okay, can everyone see my screen? You should see an index.py file. Yep. Okay, we're gonna just do a rapid fire of just some. What is going on right now? Whatever. Screw you. Okay, we're just gonna do a rapid fire big O here, just as kind of a review from yesterday. And today is really just a continuation of big O, linear and binary search, slightly more in depth. Uh, what's the time complexity here? Is it
O of
n
n
squared?
squared.
O of n squared. Yes. Here's slightly of a trick question. What's the space complexity of this function?
O of n squared.
Why?
Because my notes say two nested loops is going to be an O n squared.
All right. Pay very close attention to the words that I'm going to say once again. Pay very close attention to the words I'm going to say. What is the time complexity of function on line 5? What is the time complexity of the function on line 5? O(n) squared. O(n) squared. I'm not trying to trick you. Okay, let's try that again. The time complexity of the function on line 5 is O of n squared. Now, this is slightly a trick question. What is the space complexity of the function on line 5?
O of n.
No,
I think it's O of n squared because it takes one input and
no.
no. Okay.
Well, then it's
Time and
O of
space are
1.
not the same, right? All right, so let's go back. And this is actually something the lesson didn't do a good job of. That's why I'm emphasizing it right now. When people ask, what's the big O of a function? How many big O's is there?
One.
Oh, come on, guys. I'm just going over it right now. Every function has two big O's, right? Which one's the first one? The order doesn't really matter, actually.
Of time and space.
There you go. That's it.
I was trying to count how many total you had.
No. Pay careful attention to the questions that I ask. Okay. When someone asks for the big O of a function, you can say time or space or both. The time complexity of the function on line 5 is O of n squared. Let's try this again. What is the space complexity of the function on line 5? Keeping in mind, this is slightly a trick question. I want you to keep the following thing in mind. What's the main thing you have to remember about big O in layman's terms.
That exponents outweigh anything else.
Yeah, but if I asked you just to define what big O was, what is it?
Efficiency.
Yeah, it's efficiency of an algorithm, right? And big O just tells you how efficient an algorithm is. Okay. And really the key to keep in mind when you're trying to calculate big O is how do the outputs react as the input grows, right? What is the relationship between the output and the input? Okay, let's look at the function on line 5. As R grows, what happens to the output?
Gross.
Yeah, it grows, O of n squared, right? For space, though, what are we keeping in memory here on line 5?
Array.
Nothing.
There you go. Nothing. Nothing's being kept in memory here. R could be a million elements long, and we're going to iterate a million squared times because it's a nested loop, but there's nothing, right, that we're returning. Nothing's being kept in memory here. Right. So technically right here, this is obviously doesn't have a return statement, so it's not a properly written function. But for all intended purposes, it doesn't have one. Or you just give it the best, right? Space complexity, O of 1. Okay. Let's look at question 2. Line 11. What is the time complexity of this function?
O of n.
No, it halves every time. Line 14 is similar to math floor. Divides by 2, rounds down to the nearest integer.
So essentially it's still two nested loops.
No. This is not a loop at all. This is an arithmetic function, right? You're just dividing, right? So which algorithm, you know that on every iteration, it cuts what you're iterating over in half. What algorithm is that? Is the one used in binary search. So if you know that, you know it's O what?
O M O log
Login.
n.
O log n, yes. That's really the only thing you have to remember about the algorithm. Hey, is what you're iterating over kind of halving every time? If it is, it's log n. There's a little cheat code for you, right? All right. What is the space complexity of the function on line 11?
O of n.
Okay, let's look at O of n. If n on line 11, if n is a million, or n is 10 million, does my output grow in relation? What's being stored in memory? Does it grow in relation to how big n is?
I guess technically no, because it's
It's
still
not
only,
technically. It
because
doesn't.
it's only the number gets bigger, but the space that it holds that one number doesn't get bigger.
So ultimately, you just have how many variables regardless of how big n is.
Just the one.
There you go. So what's the space complexity of this function?
O of 1.
There you go.
Constant.
Perfect. Next function. I don't know what's going on here. Oh, whatever. Line 19, right here. Time complexity,
O of n squared.
not O of n squared, but close. There are two nested loops here, but you actually recognize the loop on line 22. What kind of loop? If line 22 stood on its own, what time complexity would that be? It's awfully similar to the one before it.
The O of n log n.
It's not n log n. That's actually the right answer to this, right? But the while loop by itself is just a log n. And you know it's inside of a for loop, so it's O n log n. It's not always going to be O of n squared. Remember, n squared assumes that the iterations are the same between the outer loop and the inner loop. That's why you have two n's. If they're different, it would be O of n times n, right? And if the inner loop is something that halves every time, we know the nomenclature for that log n. So it'd be n times log n, O of n log n. If you're only getting like 20% of this or 10%, that's fine. That's pretty normal. That means you're learning. That's okay. Don't freak out. All right. Function on line 27. I don't expect you to know this straight off the dome. That's okay. Let's see if we can get close. So I'm just going to ask you a very specific question about function 27. See if we can get close. What part of this function on line 27 is the most expensive? Which line?
What do you mean by most expensive?
Okay, when I say
Line-
most
line-
expensive means a couple different things, but ultimately it just means one.
It's line
Pin
35.
programmer,
No.
give me a second. When I say most expensive, it means a couple things. It means it takes too long to develop, like a call, right? Or it takes up too many resources, too much memory, too much compute, too expensive. So too expensive can be it's taking too long or it's too expensive. But ultimately, it just means one thing. When someone says most expensive, they really just mean money. Because a call that's taking a long time is eating up a lot of resources, probably. Right? So ultimately, that's just money, right? Yes? All right. So which line on the function on line 27 is the most expensive?
Nested for loops.
Give me a line. That's what I asked for.
31.
The 35 appending?
No,
33.
no. Don't guess. Tell me a line and tell me why you think that that's right, even if you're wrong.
Say 32 because it's a nested for loop. There's a for
No.
loop inside the for
I'm
loop.
just asking for what line's the most expensive. No one has said the right line so far.
Did you have 31
Oh,
because
yeah, I'm kind of lost already.
you're
But
taking up space?
Okay, everyone just let's take a step back. That's exactly why I'm doing this, right? When you look at the function on line 27, right? Look at line 27. Look at every single line. One of those lines is going to eat up a disproportionate more amount of resources than any other line. See if you can pick it out. You've pretty much picked out every line except for the right one. So someone's going to get it here soon, even if it is just dumb luck.
when you say it's going to eat up, like it's going to take a lot of compute power, or what do you mean by it's going to eat up a lot?
That's exactly it. It's going to take too long. It's going to eat up too many resources. That's just expensive.
So the only thing I see that's doing any type of operation is 33. the plus. I don't know.
That's not true.
Line 35.
31.
Zero pending.
No.
Yeah, then
Look
I
at,
just
we're going to
31.
stay here until you get this. Line 27 to 36. You've already called out almost all the lines, but we still haven't figured out which one. This is literally a thinking exercise. I literally just made this up, but I want you to really think about this. Right? Notice this isn't in the GitLab or the GitHub. Sorry, I work in GitLab right now, so I'm always thinking GitLab, but no, GitHub.
It's 34 because it calls
30.
itself as well.
Good, Nicholas. Is that you?
Yes.
Yeah. What's a really inefficient algorithm?
Recursive
There you go.
algorithms.
There's only one recursive call here, line 34. Nothing comes close here. So you guys weren't just a little wrong, right? You were way wrong.
Okay, so I get we were way wrong or whatever the case may be, but um, I wouldn't have known that. Right now, I'm not at a point where I know that recursive is the most inefficient. And if it was told to us before, that's something that
I think I probably said it 30 times to you guys.
I'm sure you did.
myself.
I'm sure you did. There's a lot of things that said 100 million times, but like I said, it's not a something that I've retained, but I'll definitely retain that.
Okay. So now let's look at it. And even if you don't know the nomenclature, we're going to see how close we can get to the real time complexity of this function. We know that it's amongst the worst you could possibly have because you have line 34, right? But what makes this even worse?
The recursive call is in the nested for loop.
Yes. Look how awful this is, right? This is factorial. This is the worst you can get. Look at what you have. You have a function, right, that does some kind of check here, making sure that you're not returning just like an empty list, right? Or a list that's no bigger than element one, right? Then you're trying to build a results list. Cool. But then you have nested for loops, right? And the inner loop is actually running a recursive call on every inner iteration. I don't think you could write a worse function than that one, or at least efficient. So that's the worst you're going to get. This is factorial. You're never going to see this, but it's important for you to be able to identify it and why it's bad. Questions about that? If any questions rise later, feel free to bring it up. Okay. Line 39. Function on line 39. This is another really bad one. And what tips you off that's not really great? Which line in function line 39 tells you, hey, this is, I may not know what the big O is, but I know it's terrible.
There's some people in
40
chat saying
42.
42.
Yeah.
Yeah, but what is it?
Personally returns itself twice.
Yeah. This is O of 2 to the n. This is not factorial, exponential. Also very bad. And you can tell it's bad, and it's going to be probably along the lines of exponential because you have a recursive call. Not only do you have one, you have two. Again, you don't have to be perfect, right?
Be line 42.
Yes. You don't have to be perfect. You just have to have a pretty good idea of why something is good and why something is bad at first glance. And that's going to take a little bit of time. But that's what I'm trying to prepare you for here. All right, line 45 is an easy one. It's the time complexity is just,
Constant.
yeah, O of 1. Direct indexing. This was a dictionary, it'd be the same if you grab the key. Good review? I think this is 1, 2, 3, 4, 5. Yep, that was the 6 big O nomenclatures. Cool. Let me see. All right. So today's lesson. Today's just an extension of Big O. We're going to talk about data structures and simple and binary search. What's a data structure?
Whatever you're holding your data in.
Yeah, right. Just specialized formats for organizing and storing data. That's it. That's all you need to remember. Data structure, specific format for organizing and storing data. Super, super, super important. A lot of pretty much all the applications in the world, this is kind of a big problem. And this is where architecture decisions of applications kind of come in. How you're going to organize and store all this data for efficient retrieval or efficient manipulation or efficient calculations or efficient anything. Remember I told you you weren't going to use like the 3 worst algorithms ever? Because you would just do what instead?
Modify your data structure to be more efficient.
Yes, that's it. And we'll do an exercise. I'm creating an exercise right now that I'll hand you a little bit later where you get to practice that because that's really important. All right, so data structures, just formats to organize and store data. And actually organizing and storing data is really, really, really important. I would argue it's just as important as any algorithm you're going to run on your data, simply because it's going to make it easier for you to run queries on it and work upon it, or it's going to make it very difficult. All righty. Why data structures? How do you improve program efficiency? Efficient data structures improve programming efficiency by optimizing the way data is stored and accessed. They enable quicker search, insertion, deletion, manipulation of data, contributing to faster algorithmic performance, right? For example, say you go to Netflix for the very, very first time and you go to create an account. You go to create an account. What do you think is happening behind the hood? This is a really big question. Let's see if we can get close. You go to Netflix for the very first time. You go create an account. It first asks you for a bunch of what?
Inputs.
Yeah, a bunch of inputs, right? Name, email, right? Blood type, right? You have a pet. That doesn't ask you all that, but a lot of personal information, right? You hit create account. Once you hit create account, what do you think happens to all that information that you just sent?
Maybe it's making a user class in a dictionary, something like that.
Yeah, something like that. This is a gross oversimplification, but yeah, that's what is happening, right? And it's adding it to some kind of probably data structure where it can be stored, right? But it's probably not adding it to a dictionary. And why is that? I mean, it's probably not adding it to a list. Why is it not adding it to a list?
Because trying to, or for Netflix to try to go search it, it would be inefficient if it was a linear.
Yeah, it'd be too inefficient to go search for that user, right? So you're probably stored under a specific user ID, right? Let's call it 123. You become user ID 123, and you just have a dictionary name, Guillermo, last name, Aguilar, email, whatever, 123 at AOL.com, right? And then I created my account. And then I'll probably have a key called payment. And in there, it'll be hashed or whatever. But under payment, it'll probably have my payment method saved and all that stuff, right? Gross oversimplification, but that's kind of what's happening. So why data structures are so important. The only other thing that I'll touch on here is this line right here. I guess I got to hold it. Okay, cool. Choosing the right data structure for a specific task is vital to designing algorithms that are both time and space efficient. Out of the three problems, actually all of them demonstrated this. Can anyone give me an example of one of the three problems we did yesterday that exemplifies this right here? Choosing the right data structure for a specific task is vital in designing algorithms that are both time and space efficient.
Probably the duplicate one.
Yeah, the duplicate one, if we remember that one, this one. Write a function that takes a list of numbers and returns true if any of the number appears more than once. The dictionary helps us here to check, hey, have I already seen it? Because the minute that I see it again, I return true. And if the loop finishes and I never see it, I return false. You could have done this with lists, right? You could have done it a bunch of different ways, but the most optimal way was the dictionary. You could have used a set, I believe. I think that's what we discussed yesterday. Did anyone research sets?
Actually, from that, I think it was Logan put a link to Python cheat in there, or Python cheat sheet or something, and they had it. I read it on there.
Good. How does Python access elements in a set? Anybody read that? Does it iterate? Oh, come on, guys. Someone looked at it, I know. All right, it doesn't iterate. It accesses directly. So a set is treated a lot like a what in Python?
Dictionary.
Dictionary, yeah. They're treated identical. That's why either or would have worked. All right, cool. A list. How is a list interpreted in computer memory? A list is a fundamental data structure that represents ordered sequence of elements. In computer memory, a list is often interpreted as a continuous block of memory where each element is stored at a specific index, allowing for direct access to any element. That's why when you get the last one, you get the first one, or you get the third one, you can grab it in direct time because that's just a specific slot in memory and the computer knows where it is. It kind of acts a little bit like a key in the dictionary. Same idea. All right, so what operations exist in a list? Access, insert, update, and delete. Access is just indexing an element, right? Inserting is either inserting at a specific position at the beginning or the end, anywhere really. Updating, modifying that specific list, right? Appending to it, inserting to it, or deleting. It's just operations that you can perform on a list. Can you perform these operations on a dictionary?
You can, but not in the same way.
Yeah, you can, but not in the same way. Yes. You can, you're just not iterating, right? You can insert directly, you can delete directly, right? The only thing that changes is the iteration. So honestly, you try to avoid iteration if at all possible. It's not always possible, but if it is, try to avoid it. Why? Compute. Cool. Simple search. We already talked about a linear search here, and this is just another example, right? It's iterating over a specific list and it's trying to find a target. Once it finds it, it returns, I believe, their index, and that's it. Time complexity analysis, again, you already know that. Not going to dive too deeper into that. The next one is just a binary search. What's the main thing you need to remember about any binary search? It does what? There's two things you need to remember.
Splits it in half.
Splits it in half every time. And in order for binary search to work, what needs to be true?
You got to be able to split it in half, so it's got to be even.
No, it doesn't have to be even. You could just round down if it's an odd number lane.
Oh, it's got to be sorted.
Yeah, it needs to be in order. Right? Think of a phone book. And I think that's actually, that might be the example they show in here. Think of a phone book if you're looking for like a last name Rodriguez, right? And you grab a phone book, you don't start with the A's, right? You jump straight to the middle of the phone book, right? Because you know it's in order. And that's going to be way faster if you just open the middle of it and look for your R. And then when an R, you look at the end because RO, right? That's way more efficient. Imagine a phone book that's not alphabetical. You would have to do what kind of search on it?
A linear.
Yeah, linear. You're going to have to check every single name to check if it's the name you're looking for. There's no other way to do it. Right? Think of just this binary search example in your head for a second on why the ordering of data is so important. It makes all algorithms acting upon the data that much more efficient. And ultimately, it saves money. Because right now you're doing one or two calls, your personal project will have maybe dozens of calls, right? But when you deal with real world applications that make money, you're dealing with hundreds of thousands, millions of calls, billions of calls in aggregate, a month, a week, a day sometimes, depends what it is. Yes? All right. That's one thing you need to keep in mind. I'm not going to go over this binary search because that's actually one of your challenges. So for your assignments, you're going to do a simple linear search activity, and then you're going to read this intro to data structures and algorithms, which is more or less kind of what we discussed already. This should be a pretty quick read, but the terminal learning objective is kind of what I've been telling you since the beginning, well, since yesterday. None of these concepts will be evaluated here at Code Platoon, but they will be expected of you upon reaching an interview process for your first job. That's kind of the only time you really see it. And again, those three bad algorithms, you typically won't see them out in the wild anywhere. They're too inefficient. All right, so you have two assignments for today. You have this binary versus simple search. Wait, did I put them out? I think I might have given them out of order. It's a linear search first, and then the other one. But before I give you guys a break and before you jump into your individual rooms, if you did not solve the three challenges from yesterday, I would do that first. I think they're a good learning experience, and there's a specific thing I want you to learn from each of them. Does everyone understand that? Yes? Yep. Okay. So right now it's 6:07. Let's take a 15-minute break. Let's come back at 6:23 p.m. into your breakout rooms individually. Work on the 3 challenges that I gave you yesterday. If you already finished them, you can move on to today's lesson. We'll probably do individual work for maybe 30 minutes. Then we'll come back, debrief, and then we'll do peer programming for a little bit after. That's all I have. I'm going to ask for volunteers. The assignment for today that doesn't include the 3 from yesterday are only 3 little scenarios. It's a comparison between linear and binary search. So let's just walk through all 3 of them. Does anybody want to demonstrate their, whoever has one? Anybody complete one by chance?
I finished scenario 1, just barely.
You want to walk us through your solutions?
Yeah, I can. Can y'all see my VS Code?
Yep.
Cool. So the first one, the linear search, it said to keep track of the iterations. So I set a counter for 0. Then I started my loop and checked to see if it was the target. If it is, you still count up 1 and return a message about how long it took in the item. If it's not the very first one that you check, go down, count up again. And if you don't find it, it's not in the provided data. The binary search, that one I struggled with a little bit in the curriculum. They have the code snippet, so I kind of follow along with it, and I think I got it. I made passes. So you're passing in an array and a target, but I didn't realize that for the testing, it's already sorted. And so I went ahead and sorted the list, set count 0 and it looks a high and a low. So the length of the array minus 1, and then just start splitting it in half from there. So if it hits the first time, you have a count of 1 and you're done. Otherwise, your low becomes mid plus 1 and your count goes up. And then if it's bigger, it's going to be mid minus 1. And it's just going to keep doing that as long as low is lower than high. And then it'll return not found in the target if it's not there.
Be good. Any questions on these 2? This is challenge 1 of your assignment. Yeah. If you check the test case, it does come in sorted for binary. Okay. If there's no questions, if there are any questions, feel free to just chime in here. We're going to walk through his code a little bit. Scroll up. Okay, cool. What's line 13 doing?
But out of the for loop. So it's not really doing anything.
It's not doing anything. Delete it. Okay, cool. Is there any other improvements we can make on this code? Or is it perfect?
it looks good, but for what the examples we're trying to get, we have to use the enumerate to actually pull out the index. That's what I was just realizing in my own code, right as we broke out of the rooms.
Say that again.
The examples at the bottom when it's making the call for it, the print statements wants the actual index of the number where the target's actually found at. So we have to adjust the loop to change it to pull the index rather than just the number.
Got it. Did you get that, Scott?
No.
Whoever said that, can you walk them through it just on the linear search one?
Yeah, you see right there, line 52. It
Yes.
says scenario 1, linear search, target found at index. And then so that first result when we return should be the index number and then the number of steps. I didn't finish it because I actually just realized it myself and wrote mine pretty much the same way you have yours written right now. So how to tell you exactly how to do it, I don't know how to do that yet.
So
Other than the enumerate loop.
Don't necessarily need the enumerate loop, but you could use the enumerate loop. Let's do this together. We're just going to update line 6. We're going to update line 6 right here live. Which loop would you like to use, Scott?
for the linear search,
Yes.
just a for loop, I guess.
Okay. But you can't use this for loop because we need the what?
You still need to grab the index.
Yes. So just use a for I in range. Unless you're comfortable with enumerate, which you can use that too. You don't need it though.
So is that going to be nested inside the for?
No, it's going to replace your regular
Okay.
for loop. So for I in range, missing length right there, length of R.
Oh yeah.
Inside the parentheses. Doesn't have to be -1, it's just length of R. And then you're missing one more parentheses and a colon. Okay, cool. And then just fix your conditional and those template strings. And this would be just R what?
I.
Yep. It'd be RI, right? Not just I. RI in the conditional if this number is the target, right? Equals the target.
You're saying, yeah. I thought you were saying the letter R, not
Mhm.
like
Yeah, no
array.
worries. Cool. And then don't worry about the string. It's fine. We assume that you can fix that string. Okay, so it would look something like this. The only other thing that I want to point out is look at line 9 and line 12. What's happening at line 9 and line 12?
You can just move the count outside of the if and else statements at the top of the for loop.
Perfect. Do that. And then if you fix the strings, this would be the right answer. Does everyone understand why we moved count up?
It's a failed test because it's not in the requirements, or else I'm misreading this.
No, don't worry about that. Let's just focus on why we moved count +1.
Readability.
No, it was readable before.
It doesn't need a conditional. They both were count plus equal 1. So
That's the answer. It's not dependent on any conditional. The minute that you go into the for loop, that is an incrementation. That is an iteration. So just increment right away. You also don't duplicate that line of code. Good. Let's go down to the binary search. This looks good.
It
What
should.
can you?
It's cookie cutter out of the curriculum.
No worries. You don't need something on line 19. Do you know what that is?
The -1.
No, you need a -1 there. That's fine. Line 19, there's something that he has he doesn't need.
The parentheses. Oh,
Yeah. The parentheses are not doing anything.
With the outer ones.
Yeah. Cool. What are the parentheses doing on line 22?
What is the what doing?
What are the parentheses doing on line 22?
Just making it more organized in my head. The same reason they were on line 19.
Okay. So that's a great
Using
answer.
PEMDAS.
Yeah. So, okay, let's get to that. So his answer was actually really good. I knew that that was what he was going to say, right? In his head, it makes sense here. But if you follow order operations, you actually don't need them there here because division comes before addition. But wait, division comes before addition, so you do actually need them here. Never mind. It's the opposite of that. So on line 19, you didn't need them because they weren't doing anything. But on line 22, you do need them.
So as far as like in an actual like job, is it frowned upon to have the parentheses there anyway, or it's just like not needed, so don't do it?
It's frowned upon. It's about, people always talk about code quality, right? When you look at superstar rockstar code, when you read it, you're like, oh man, I would have never thought of that. That's really awesome, right? But when you read bad code, it's really obvious, right? So yeah, you wouldn't use it. It's kind of like using the like reassigning a variable after every condition and then returning that variable at the end when you could have just returned early. Or sometimes you'll see this. Here's a tip too. When you look at people's codes, if they have more than 2 nested conditionals, that's wrong. And that's just a code quality thing. It's really hard to read that, right? Ideally, you only have 1, sometimes 2, but that's getting really hard to read. Let's see if I can give you an example of that later. But think about all the code that you've written. Anytime you're nesting more than once in a conditional, there's probably a better way to do it. You don't have to say anything. Just think about all the code that you've written up to this point. Anytime you have like an if, and then inside of there, there's another conditional, there's always a much better way to write that. That's really hard to read. You wouldn't write it that way. Really, 1 conditional is about the max if you want to be really good at it. That's just a good general rule of thumb. I hope that made sense. Yes?
Yep.
Okay, let's look at binary search. You're kind of running into the same problem here with count again, right? So how do we fix that?
Move it back out of the
Yeah, it's the same issue. Yep. Once you move it, you're good. Okay, that works. This is great. Thank you so much, Scott. Did anybody get to 2 by chance?
I did.
Share with us, Logan, please. All right, yeah, just walk us through it.
For the linear, I initialized count. I used a for I in range, just like we did on the last example. So range length, word list, and then did the count above the conditional, and then grabbed the actual value at the index. If that equals the target word, return that value and the count that it took, otherwise return false.
On line 42, inside the second parenthesis, right to the left of word, inside the parenthesis to the left of word,
Right here.
put a 0, comma, All right, go to the end of word list, comma, put a 1. Put length around word list and then delete the outside version of it. Now delete the outside function of length. And delete that last, I think you deleted one too many parentheses on range. You're missing after range,
Oh,
put
yeah,
one
yeah.
parentheses. Yeah. Okay. All right, stop right there. You don't answer this, Logan. Someone else, tell me what changed on line 42. Like what's inherently different in this code compared to what he wrote?
This one you're given the increments at the end, 1. You're starting at 0. So you're given the full I guess the conditions of the
Yeah,
of
but
the
functionally, is it any different? Is this
well,
is this code gonna run any different than what he had before?
no, I think it stays the same because some of that is like automatic without request, right? Or simplified, I guess. So like for
Implied
instance,
is the right word here. Okay. So the way that he wrote it, right? It's implied that you're going to start at the beginning, you're going to go to the end, and you're going to go by ones, right? Here, I made it explicit, but when you don't make it explicit, Python reads it as, hey, I'm going to run it like this from the beginning to the end by ones, right? If I wanted to go backwards here, right? Logan, do you know how to do that on line 42?
Maybe replace this with a -1.
You're pretty close. Remember the 3 things, right? It's start,
Start,
stop,
stop,
step.
step.
All
Mhm.
right. So how would we go backwards if we wanted to do this? Remember, start, stop, step. Doesn't change at all.
So this would be 0 then?
No, start,
would
stop,
link,
step.
I was gonna say, would linked word be in the beginning?
Yeah. Let's start at the end of the word.
Like putting linked word list on the start.
Yeah. Length worthless, comma, -1, -1. The last 2 are -1. Does anyone know why?
Well, the start would be, or it would be the -1 would be start stop because that's going to be your stop, the -1, and then your step is you're going -1, so you're going.
Yeah, but you're not really describing what they are. Why are they -1?
-1's the end of the list.
Why is it not 0?
Positionally, 0 is at the beginning.
Well, I mean,
No. Look
zero
at its
is
position. No, look at its position. This is the stop. Why is it -1 and not 0? Because
you're talking about on the step on the step
on
parameter.
either, actually, this applies to both.
Because 0 is your index, it's the beginning of
No, look at the
I don't know how to
location of it.
describe it. Yeah.
There's a crucial piece to this, Jose, and everybody else. All right, you start at the beginning, right? But we're going backwards. So we're telling it start, stop, step, start at the end at -1 index, and go backwards by 1, right? This is an important thing to understand, right? This is reading it as, hey, the ending point is non-inclusive. That's why it's -1 and not 0. Right? If you put 0, it actually stops at 1. If you put -1, it stops at 0, which is where you want it to stop. -1 tells me, hey, go backwards. You can go backwards by 2 if you want. But that's how you read that. Small nuances in Python. I just wanted to draw attention to. If that didn't make a whole lot of sense to you, just mess with your loops. Eventually, you'll figure it out. But I just bring up these little moments right here so you can kind of get a better feel for Python as a language. All right, that's great. That's linear search. Go ahead, Logan. Give us your binary search here with assorted words.
Yeah, it's going to be similar to the last answer as well. Initialize my count, Then I guess we're initializing the low and high and using a while loop. Again, putting the count outside the conditionals and just divide and conquer until one of these things is true and then return how many times that took. The one thing I didn't really get, so down here in my elif and else statements, we're resetting the values of low and high so that the next time it loops, it looks at the next section. But in my code editor, it says it's unused. Is that just because it's not big?
Say that again.
Yeah, so in my elif and else statements down here, I'm resetting the value of low and high so that each time it takes like the next half chunk and looks at that instead. But in my code editor, when I hover over it, it's kind of like gray.
Yep.
It says it's unused. Usually I see that like if I name a variable and then I don't do anything with it. But I don't know exactly why it's happening in this case. Is it just because I'm not doing anything with it like lower than it's currently being used in my conditionals, or?
Can anyone figure this out? That is strange. It's definitely used, right?
I guess
Line-
would be low and high. Low and high is the same in the first line. And then it's different when you're Nelson it. Maybe not.
It might be, you know what I just thought of? I just realized if you look, it says Firefly. It might be because I'm trying Firefly and it's still in like alpha. Maybe I should just go back to what I was using before.
I don't know what Firefly is.
Firefly is Meta's open source Python syntax thingamajig.
If you change the variable, just make them direct line variables on line 53 and don't use the fancy syntax. Does that change it? I'm curious.
You mean?
No. Leave that alone on line 53. Just change line 53 and line them up. Just keep them in one low and then high red at the bottom.
Oh, you mean?
Don't define them like that. Just define them normally.
So just essentially.
Yeah, I shouldn't be doing that. I'm not quite sure why that's happening, actually.
Yeah, I'll switch the extension that I'm using for that, and that might just be it.
Yeah, this looks right. So I don't think that. I think that's probably the extension is my guess. I mean, the other way you had it would have been fine, but I don't know why it's doing that because it's definitely defined, right?
Yep.
All right, good stuff. Awesome. Anybody get to 3? That was probably a lot. I don't imagine anyone probably got to it, but if someone did, I'd like to take a look. How is scenario 3 different from the 2 scenarios we just did? How is it any different? Just after reading it.
There's a target.
There is a target, but we had a target before, right?
Yeah.
That doesn't really look that much different. So yeah, definitely give it a shot. So what's going to happen now is, yeah, the 3 is not that much different. What's going to happen now is I am going to post. Give me 1 second. I'm going to post to groups first, and then I'll describe it. I can never get to it. All right, cool. Groups. And I posted the groups in the India and evening and weekend channel. The first thing I want you to tackle in groups is problem number 3. And between both of you, whoever hasn't got to it, right, or whoever has done less of the programming thus far, you should start doing it. And the other person can shoulder surf / guide them through the program, through the challenge. Make sense? So problem number 3. The next thing you're going to do is right underneath the groups that I just posted, I'm going to post a little challenge where you're going to write a couple functions, but also refactor some of the data. And that'll be the main group project that you will work on. Does that make sense? Yes? Alrighty. One really important thing. I don't know if I've mentioned in this class, but if I did, forgive me. I'm going to go ahead and mention it again. When I was learning to program, I found this guy on YouTube. I think some of you may have heard this, but I'm going to say it again. I found this guy on YouTube, and he was showing me how to code stuff, like do coding challenges. And he said something really important that I took with me forever that has paid a lot of dividends in my career. And now I'm going to share it with you. A really important lesson. Don't guess. Programming is so big, right? Borderline intractable. You're never going to get it right if you guess. There's just too many variables, right? That's what I learned from him. I wish I could remember his name. He's probably one of the famous software engineering YouTubers. I can't remember. But that's what he said. Don't guess. If you think the answer to something is X, say, I think it's X, at least in your mind. You don't always have to say it out loud, but in your mind, I think the answer to this is X for the following reason. And then you figure out if you're right or wrong. If you're wrong, you figure out why you're wrong. And then you improve the mental model that you have in your mind and become a better developer with every single iteration. Does everyone understand that? That's by far one of the most important lessons that I've ever learned in this field. Never guess. Even if you're wrong, right? At least know why you were wrong, and then you will improve on the next iteration, right? You can tell that sometimes I get annoyed when people guess because I take it very personally. Do not guess. This will help you. I promise you. That's probably one of the best tips that I have that I can impart upon you. Don't guess. Know why you say what you say. All right. Why you think something does what it's supposed to. All righty.